Welcome. What I have discussing in the previous class is about of that conformations of cyclopropylene rings. So cyclopropylene ring has that two conformations we have, mainly that is bisected and perpendicular conformations. It means that one is perpendicular conformations, another is bisected conformations. Conformations with respect to carbohydrates. Okay, and this is also with respect to carbohydrates. So if that perpendicular in the sense, let's say here it is the carbohydrates, and here we have the positive charge, and that is the cyclopropylene ring is like this here. Okay, so this is called the perpendicular conformations. Here also this cyclopropylene, so orbitals are bent orbitals are there. Okay, and for bisected conformations, that is here carbohydrates and like this, and here we have that cyclopropylene ring like this. Okay, here also that is in the bend, overlapping is there. So that I have discussed in the previous class, that carbocation means that it has that vacant free orbitals. Here also let's say vacant free orbitals. Now that if it is perpendicular conformations with respect to carbocation, then what happened that it has that expanded electron density, but this expanded electron density that is not in a proper orientations with that vacant free orbitals of the carbocation. So electrons from here not able to go to this p orbitals, means that no proper amount of electrons will go to this vacant p orbital. I mean, it means that they may go like this, they may go like this, means that they are not going to this vacant p orbitals if it is in a perpendicular conformations with respect to carbohydrates. But if that is a bisected conformations with respect to carbohydrate, here what happened that electrons are directly going to this vacant p orbitals. Okay, so here that proper electron transfer will happen here. Okay, if it is bisected conformations with respect to carbohydrate, which is bisected, that cyclopropylene ring, cyclopropylene ring is bisected conformations. Cyclopropylene is perpendicular conformation with respect to carbohydrate. So here what happened that since that cyclopropylene rings and the carbohydrates are in a proper orientation, so that electrons, that proper amount of electrons, can transfer to the vacant, or I can say that more electrons can transfer to the vacant p orbitals of carbohydrates. Here, since there is no proper orientations of this cyclopropylene ring with this vacant p orbital of the carbohydrate, so no electron from cyclopropylene ring can transfer to vacant p orbitals, vacant p orbital of carbohydrates. So what is in that this is this case, this is less stable. So this less stable carbohydrates, because the electrons are not properly transferring to this vacant p orbitals from the cyclopropylene rings, that's why this carbohydrate is less stable, whereas this carbohydrate is more stable. Okay, so that things that I have discussed in the previous class. So today actually what we are going to discuss, that applications where we will find this applications related to these perpendicular conformations or bisected conformations. Okay, so today class we will discuss about of that applications. So here we will see that the applications that if it is that applications of bisected and perpendicular conformations. So if like how they ask the questions, they compare the rate of the solvolysis. Okay, if A and B, in this case which where that rate of the solvolysis will be high. So rate of the solvolysis in the sense that which carbocation is more stable. So here which is more stable, you see that in this case this cyclopropylene ring, okay, and this ring is outside this ring. So if like that things we will get, then we will say that this is the perpendicular conformations. Perpendicular conformations with respect to carbocations. But here you see that this cyclopropylene ring is inside this inside this ring, this whole ring. Okay, so this type of ring is the what you see that these are the bisected conformations with respect to carbocations. So these are the bisected conformations with respect to carbocations. So now they ask that which carbocation is more stable between A and B. So stability of carbocations here. So in between this, what we see that since this is the perpendicular conformations, so electrons from this cyclopropyl ring will very less amounts. Okay, very less amount will come to this carbocation. So this carbocation will be less stabilized. Whereas here the 2CH3 is there. Okay, so they will do that inductive effect, and this due to this inductive effect, this carbocation will get more stabilized than this because here there are very less electron because this cyclopropyl ring is in a perpendicular conformation. So if here if you calculate compare the stability of carbocation, then what is that B is more than A. Okay, similarly for this case, here what we seen that this is the perpendicular conformation, this is the bisected conformations and this is the normal. Okay, now if you compare this, then if it is bisected conformations, on that case here more electrons will transport to this because of that expanded electron density. So here the stability of carbocation H A is greater than B. Okay, so similarly here also if you check that here also if you check that stability of the carbocations. Okay, so here what is in that 3CH3 is there, so this is the 3-degree carbocations, and when this carbocation is uh, let's say in this ring, so how many this type of that bridge are there? Okay, so this bridge join atoms, so here 3, but here 2, and here is 1. So if this is increases, then that amount of this carbocation is stable. So here if you check the stability of carbocations, then first will be A, then B, then C, then D. This is the order of stability of this carbocations. Okay, now moving to the next, so we will look that rearrangement of the carbocations, the molecular rearrangement. So whenever you see that carbocation cases, next. Whenever carbocation case, okay, so if intermediate is carbocations, so if intermediate is carbocations, then always look for that any molecular rearrangements, because if intermediate is carbocations, that carbocation always wants to go to the more stable carbocations. So we have seen that stability of carbocations. stability of carbocation we have seen that is 3 degree carbocation is more stable than 2 degree than 1 degree. Okay, so this we have seen. So whenever intermediate is carbocations, okay, or whenever carbocation is poor, then always look for that molecular rearrangements. Molecular rearrangements. Okay, so this will play a very important role if intermediate is carbocations. Okay, molecular rearrangement will happen. Okay, what I mean that if intermediate in any reactions, if we see that if intermediate is carbocation is forming, then we will look for that molecular rearrangements. Why I'm saying that? The okay, so this molecular rearrangement that depend on the two factors. Okay, this molecular rearrangements it depend on the two factors. One is the structure of carbohydrates, another is it depends on that this is first factor it will depend, and second factors it depend on that nature of medium. Okay, that is whether it is nucleophilic mediums or this is non-nucleophilic mediums. Okay, so what we see that whenever we see a intermediate is carbohydrates, we always go for that molecular rearrangements. So that molecular rearrangement that depend on first is that structure of carbohydrates, and next it depend on the nature of the mediums. How I'm going to explain that. See, if you have that carbohydrates, okay, that stability will be 3 degree, then 2 degree, then 1 degree carbohydrates. Okay, so now if we have that is medium is let's say the first medium is non-nucleophilic. This points this is the first point. Medium is non-nucleophilic. Okay, medium is non-nucleophilic. Then what will happen in this case? Either this is 1 degree carbohydrates, okay, or 2 degree carbohydrates, or it may be 3 degree carbohydrates. Okay, 1 degree, 2 degree, 3 degree, any carbohydrates that it will do the rearrangements. Rearrangement happen, and that rearrangement to get the I can write here maximum possible rearrangement will happen. Possible rearrangements to get most stabilized carbohydrates. Okay, so it means that if medium is non-nucleophilic, okay, if medium is non-nucleophilic, then either it may be 1 degree, 2 degree, or 3 degree. Okay, all the cases of this carbohydrate, it will do the maximum rearrangement to get the most stabilized carbohydrates. Let's say we have that carbohydrates like this. Let's say here we have H is there, and let's say here we have that CH3, and let's say here we have that CH3, then CH2Cl is there. Okay, now if medium is non-nucleophilic medium is there, then what will happen here that okay, let's say here also CH3 is there. So what will happen here that this is the this chlorine will leave, so it means that they may give so one reagent like AgNO3. Then what will happen, this will take this chlorines, because whenever you see that this AgNO3, whenever you look the metals, then what you will see that this metal has the vacant p orbitals. Okay, so this is actually form that Ag plus and NO AgNO2 minus. So whenever you see these metals, then this have that vacant p or vacant d orbital. So this is one type of Lewis acid. So this Lewis acid, what it will take that here the lone pair is there, so this donate electrons to this vacant p orbitals of this Ag. Okay, and then here Ag will be there, and this Ag will take this, and we will get that AgCl. Okay, so like that. So what it will form, that carbon CH3 and CH3, and here CH2 positive charge will form. So this is the 1 degree carbohydrates. Okay, now what will happen, that in this case, since this is the 1 degree carbohydrates and medium is non-nucleophilic, so here the rearrangement will happen. It means that methyl shift will happen. This will shift to here, and we will get that CH3, and here you will get positive. Here we have the CH3. Okay, after that so this amount of carbohydrate will happen, means that this is 1 degree and it shifted to the 3 degree carbohydrates. So if medium is non-nucleophilic, it may be 1 degree, then also rearrangement will happen. 2 degree, then also rearrangement will happen. At 3 degree, then also rearrangement will happen. Let's say if we have that 3 degree carbohydrates, 3D carbon, let's say this type of groups is there. Let's say we have that CH2 positive charge is there. Okay, and here maybe hydrogen is present. Yes, here hydrogen is present. So in this case, what that this is the 1 degree carbohydrates. Okay, so now if medium is non-nucleophilic, then what will happen, that we know that migratory aptitude that is first, that is we remember that Hartford. Okay, so H stands for hydrogen, then pH stands for phenyl, and R stands for alkyl group. So what that migratory aptitude says, that first hydrogen will shift, then phenyl will shift, then alkyl group will shift. So here that H is there, also this R groups also there, but which will shift, first preference will be the H. So what you will do, that this H will shift to this. It means that what we will get here, these groups, this 4 member rings. Okay, and here we will get CH3, and here we will have the positive charge. We see that this is the 3 degree carbohydrates. Okay, but now what will happen, that since this is the 3 degree carbohydrate, but angle is what, that is 90 degree, and we know that for a carbohydrate the angle needed is 120 degree. So although this is 3 degree carbohydrate, but angle is 90 degree. So for carbohydrate it need angle that is trigonal planar shape. So I have discussed in the past class. So it need 120 degree. So here again that rearrangement will happen, because this is the non-nucleophilic mediums. Okay, so if it is a non-nucleophilic medium, then maximum rearrangement will happen. But if it is nucleophilic medium, then this is happened from a 2 degree to it will shift to the 3 degree. Okay, after that directly that whatever the nucleophile is present, let's say water is present, then that water is going to, this water will attack here, and we will get the products like this, OH. Okay, if medium is nucleophilic, but if medium is non-nucleophilic, then maximum possible rearrangement will happen, even though it is a 3 degree. So nucleophilic means that rapid rearrangement will happen. Within that, whatever you will get the stable carbohydrates, then actually at 1 degree carbohydrate never the reactions will happen. Okay, that has to be either 2 degree or 3 degree. So this is already 3 degree and nucleophile is there, so that will do that. But here that non-nucleophilic is there, so this again do the rearrangement. So what you will get here, that you will get here 1 2 3 4 5, because here angle is problem, so it will shift to that more angle, so it will going to get that 5 member rings. Okay, so 1 2 3 4 5. Okay, so here what will form, so 1 and 3 is going to make the bonds, 1 3 4 5 and 2. Okay, so this is the positive charge. Okay, so this amount of rearrangement will happen. So how I say this is a positive charge, So 1 and 3 is going to make the bond. Hmm? 1 and 3 is going to make the bond. And what we know that if it's a positive, then this is the negative. Okay, this is the positives, then this has to be negative. And so I'm making that 1 and 3, I'm making the bond. Okay, and this bond is going to break. This bond is going to break. And you know that if one bond is there, then bond means positive and negative, that represent a bond. Or if you have the two electron, that represent a bond. Okay, so this I want to break. So if I want to break, then one I have to give positive, one I have to give negative. So since already positive is there, one I will put the negatives. Okay, and now this one and this I make the bond. It means that here positive charge will remain. Okay, so that's why I put the positive charge here. So this type of carbon, this 5-member ring will form. Okay, and now that, so if non-nucleophilic, then that it will stay up to here. Okay, so now the question is that here it was getting the 90 degrees, but it will become the 5-member rings, then here also the it will become the less than 90 degree. Actually it is not exist in this form. This is the planar form. Okay, this is the planar form. So 4-member ring that actually exist in the same planar form. Okay, this 4-member rings, whatever that cycle that is exist in the planar form, whatever this, that is actually exist. But in case of the 5-member rings, 5-member ring, what we see here, this is the planar, but actually this is exist, but actually exist in envelope forms. Or I can write here 4-member rings that is exist in planar. That means this. So this is exist like this. But if it is 5-member rings, that is this type of structure. But this exist, actually that is exist in envelope forms. That in the sense that is going to be like this envelope forms, and this is the non-planar. It means that one is going to be the outside of the planar. Okay, and this angle, that angle is near about of 120 degree. So that's why that for that is shifted for 4-member to 5-member rings, because in 5-member rings it's getting that more angles. Okay, so here that it is actually exist in envelope forms. Okay, that's why here this carbocation is shifted to that 5-member ring. So here it get that more angles. Now this carbocation is stable. So whenever this is 3-degree carbocations, and if it is 4-member ring, then that do the rearrangement, because here that is non-nucleophilic. Okay, so the maximum rearrangement will happen. Similarly, if we have that 6-member rings, then we know that 6-member rings, this cyclohexes, this actually exist in the chair form. Okay, this is also non-planar. This is planar, that what we see, but actually it is non-planar, and that is in the chair form. Okay, so that's we has to keep in mind. So what I'm saying here, first point, that if it is a non-nucleophilic, okay, this point has to remember that if medium is non-nucleophilic, then maximum possible rearrangement happen to get most stabilized carbohydrates, whether it may be 1 degree, whether it may be 2 degree, whether it may be 3 degree. Okay, so that's what I explained here. Okay, whether it may be 1 degree or 2 degree or 3 degree, if it is non-nucleophilic, then the maximum rearrangement will happen to get most stabilized carbohydrates. Next point is, if medium is nucleophilic, In this case, what will happen that if carboguidance is 2-degree carboguidance or it is 3-degree carboguidance, on this case, no rearrangement will happen. Okay, no rearrangement happen and direct nucleophile will attack. If it is 2-degree or 3-degree carbohydrates, if medium is nucleophile, okay, and this is the A. But if it is 1-degree carbohydrates, if it is 1-degree carbohydrate, then what happened that rapid rearrangement will happen. Rapid rearrangement. What do you mean by rapid rearrangement? If it is 1-degree carbohydrate, then that shift to that whatever that quick rearrangement will happen. Okay, whatever the quick rearrangement means, it will not do the rearrangement so that it will get maximum stabilized. No, that will not happen. It will quick rearrangement will happen. Means anyhow it may going to get 2-degree or it may be 3-degree. Okay, quick rearrangement in the quick rearrangement means that from 1-degree to either 2-degree or 3-degree. Okay, whatever it may be, 2-degree or 3-degree carbohydrates will happen and then nucleophile will attack. What I mean, actually at the 1-degree carbohydrates, nucleophile will not attack. So if it is 1-degree, that either it will go to the 2-degree arrangement, means whatever the quick rearrangement possible. Okay, so 1-degree that may going to shift 2-degree or 3-degree, then nucleophile will attack. That's the examples what I have explained here. In this case, this is 1-degree carbohydrate. Okay. In this case, this is 1-degree carbohydrate. So here nucleophile will not attack. So quick rearrangement will happen. That is, it shifted to 3-degree carbohydrates. Then that nucleophile will attack and you will get the product. Okay. So if medium is nucleophile, then if it is 2-degree and 3-degree carbohydrates, then there will be no rearrangement. Direct nucleophile will attack. But if it is 1-degree carbohydrates, then this 1-degree carbohydrates can shift to 2-degree or 3-degree, whatever the quick rearrangement, whatever the quick possible rearrangement that will happen, and then nucleophile will attack. So this is about of that molecular rearrangements of carbohydrates. Okay, so whenever we look the carbohydrates as an intermediates, then we will go for a molecular rearrangements. Okay, and that molecular rearrangements, these are the two cases. One is in the nucleophile, if it is nucleophiles, another is if it is the non-nucleophiles. Yes. Okay, so these things I explain here. Now we will solve that examples to get more clear. Let's say this example is here. Let's say this example. So this I already explained. So whenever you see that AgNO3, okay, this type of examples, then this whenever you see that metal means this is actually going to Ag plus and NO3 minus. Okay, so whenever you see this metal means they have that backend d orbitals, and since they have the backend d orbital, backends means they actually need electrons, so they are actually called the Lewis acid. Lewis acid means which accept electrons. So this accept electron, here we actually what we see that Ag plus is we will get, and this has the lone pair, so this will share. After that what will happen that this AgI will be removed. So what we will see here, see CH3, here we will have that CH3, and here we have that CH3, then here we are going to get CH2 plus. Okay, and since this is the nucleophilic mediums, okay, this is the nucleophilic medium, so very rapid rearrangement will happen. This is a 1-degree. At 1-degree there will be no nucleophile attack. For nucleophile attack, that either it has to be 2-degree or 3-degree. So let's do the rapid rearrangement. What is the maximum possible? This can shift here. So here we will have CH3 and CH3, here positive charge, and CH2. This is going to be CH3. Now that nucleophile will attack. So here what we see this Here we will have that OH and CH2 CH3. Okay, so this is shifted to 3-degree carbohydrates. So that's what I say, that if nucleophile is there and if it's 1 degree, then rapid rearrangement will happen from 1 degree to 3 degree, or it may be 2 degree also, if whatever the rapid rearrangement possibility is there. Okay, so this is the answers for these questions. Now moving to the next examples. For this, what we see that here, this is the non-nucleophilic medium. So if non-nucleophilic medium means, what we see that maximum possible rearrangement will happen. It means that here SbF5. So Sb is again a metal. So what I say is that if metal not, okay, so they actually always want to confuse. If metal is there, metal is present in reagents, so always look for Lewis acid, because they have the vacant d orbitals. Okay, they have the vacant d orbitals. So if metal is present, then always look for that Lewis acids. So in this case, what we've seen here, so on this we are looking for these examples. So CH2Cl, here what will happen, that maximum, since this is the non-nucleophilic, so maximum possible rearrangement will happen. That means that this is going to be like this, and this will take means this will share that lone pair electrons to this vacant d orbitals, and then this will remove SbCl will be removed. It means that here I'm going to get that CH2 and carbocations, and this is the 1 degree carbocations. Then for 1 degree carbocations, if it is non-nucleophilic, then that here that maximum possible rearrangement will happen to get most stabilized carbocations. So here what will happen, that here hydrogen is there. So remember that migratory aptitude, Hapur. So first hydrogen, then phenyl, then alkyl groups. So first hydrogen is there, so hydrogen will migrate. So that means this will happen here, and this is going to be the CH3 and positive charge. Sorry, CH3, here we will have that carbocations. This is the 3 degree carbocations, and we see that 5-member rings that is actually exist in the envelope forms, and that angle is nearly about of that 120 degrees. So here that it will get most stabilized carbocations, so it will remain here. Okay, now moving to the next questions. In this case, this is the 6-member ring. So 6-member rings, that is again SbF5 is there, so it will take these chlorine atoms. So here we will get the positive charge. Okay, the positive charge. But now what we see that the maximum possible rearrangement will happen, because here also non-nucleophilic medium. So here again the rearrangement will happen, means it will shift to the 5-member rings. So that means that count the number. Let's say here 1, 2, 3, 4, 5, and 6. So what will happen, that this 1 and 3 will make bond. So if what we say that it is positive, and this has to be negative. If we want to make bond, then this has to become positive. So you know that bond means positive and negative will make bonds. So if it is positive, then this has to be negative, and here also bond is there, and if it is negative, this has to be positive. So that is going to be a 5-member rings here. Okay, now what you see in that, here let's say 1, 2, sorry 1, then that form to the 3, then 4, then 5. Okay, then this is 6, and at the 1 here 2 is there, and 2 here positive charge will be there. Okay, so this will form here. Okay, so you understand that this will go to 1, 3, 4, 5, 6, this will make bonds, and this is the 2, and here positive charge there, so that will remain a positive charge. Now this is again, this is become a 1 degree carbocation. So because this is the non-nucleophilic, so maximum possible rearrangement will happen. So this again it going to do that. Here hydrogen is there, so again rearrangement will happen, and this is going to be the CH3 and positive charge. Okay, so this is going to be the final answers for this question. So it is shifted to the 5-member rings. Why? Because here it is getting that angle also it will get, also the inductive effect also it will get. So maximum stabilized form it will be shipped. So whenever it is a non-nucleophilic, always look for that maximum stabilized, maximum possible rearrangement to get the most stable carbocation. But if it is a nucleophilic medium is there, then rapid rearrangement will happen. Means we have to do rearrangement only if it is a 1 degree carbocation. If it is a 2 degree or 3 degree, then we will not need to do the rearrangement if medium is nucleophilic. Okay. Now what we see that here the medium is nucleophilic, because CH3COH that is exist as CH3CO minus plus H plus. Okay, because this is the acid that we have seen that ionic equilibrium, so that is actually exist in this form. So what I will do here, that this is the nucleophile. So what happened that, so since this is a nucleophilic medium, so very rapid rearrangement will happen. So this is the leaving group, so that is going to leave here, that is going to be like this. Here we will get the positive charge, and now this is the 1 degree carbocation, this is the 2 degree carbocation. Okay, and if nucleophilic and 2 degree carbocation, then there will be no rearrangement, direct nucleophile will attack. It means that CH3CO minus, this is going to attack here. That means we will get this product. This is the final answers for these questions. If it is non-nucleophilic, let's say non-nucleophilic mediums, then what will happen that here we get that positive charge, then here we have that hydrogen, so that hapor will be do that, then that means migratory aptitude, so this is going to be shaped like this. Here we will get the positive charge. Okay, so this is the rearrangement will happen because this carbocations get stabilized from this also, if it is the non-nucleophilic, but here the nucleophilic medium is there. So this is the final answers for these questions. Okay, now moving to the next questions. In these questions, see that here if that AgNO3, it means that it will take that this is Ag plus, and here that is going to shift here. So actually it should happen like this. It should happen like this, but this will not happen. Reason that this carbocation is forming at the bridge positions, so there will be no carbocations will form at bridging positions, so it will not happen. So this is going to be the no reactions, because carbocation is forming at the bridging position. So if this if carbocation is forming in bridging position, then that type of reactions will not happen. So today, after this, in the next class we will discuss about of that name reactions related to the carbocations. Okay, thank you.